So let us derive the expression for the field strength due to uniformly charged body. Here the body is nothing but, here my imagination is sphere, uniformly charged sphere. సో చార్జెస్ స్పియర్ అన్నాను కానీ అది కండక్టింగా నాన్ కండక్టింగా ఇందాక అనుకున్నట్టుగా మనం చెప్పలేదు నేను. సో ఫర్ ద బెస్ట్ కేస్ నేను ఏం చేస్తానంటే ఫస్ట్ కండక్టింగ్ స్పియర్ అన్నట్టుగా తీసుకుంటున్నాను. దిస్ ఇస్ ద కేస్ 1. సో యాజ్ షోన్ ఇన్ ద ఫిగర్, అండ్ వీ నో దట్ ఫర్ ఎ స్పియర్ we can say that at every point the radius of curvature is uniform and it equals to the radius of the sphere. సో స్పియర్ అన్నప్పుడు ఏమిటంటే ప్రతి పాయింట్ ఆన్ ద సర్కంఫరెన్స్ ఆఫ్ ద స్పియర్ ఇట్ ఈస్ అట్ ద ఈక్వి డిస్టెన్స్. దట్ ఈక్వి డిస్టెన్స్ని క్యాపిటల్ ఆర్గా తీసుకుంటున్నాం ఇక్కడ. హెన్స్ సో ద గివెన్ చార్జ్ విల్ హ్యావ్ ఎ యూనిఫామ్ సర్ఫేస్ చార్జ్ డెన్సిటీ ఆన్ ద సర్ఫేస్ ఆఫ్ ద స్పియర్, and the surface charge density for this sphere having the radius capital R is given by a sigma as q by 4 pi r square. Sorry, charge upon surface area q pi r square అని చెప్పేసి అంటున్నాం. let it be, this is equation 1 అనుకుందాం. So from this figure we can say that the charge given to this sphere, it is uniformly spread on its surface, isn't it? So here by symmetry we can see that the direction of electric field is radially outwards. Because the positive charge, the field intensity is radially outwards. We studied that one in the classroom, right? During the class we discussed that. So it is radially outward direction in the surrounding of the sphere itself. So it gives a feeling that it is being originated from the center of the sphere like a point charge. So my intention is very clear here. So for the conducting sphere, I can assume that the total charge is supposed to be concentrated at a point, isn't it? So this point is very very important. ఒకసారి జాగ్రత్తగా గుర్తుపెట్టుకోండి. మొత్తం ఛార్జ్ అంతా కూడాను ఎట్ ద సెంటర్ దగ్గర ఒరిజినేట్ అయ్యింది, లొకేట్ అయ్యింది అని తీసుకుంటాను నేను. Because the expression for the conducting sphere and the expression for the field intensity due to a point charge is almost equal, right? So thus for uniformly charged sphere, we can say that for outside points we can assume that the whole of its charge is concentrated at center. So the field strength at an outer point situated at a distance x, suppose if I am taking a point P here which is at a distance of x from the center of the sphere, I can say x is the distance. So for I can write directly x greater than r, the expression for the E is 1 by 4 pi epsilon naught, that is capital K Q by x square. So for a points on its surface, which means if let x is equals to r, I get the expression as k cube by r square. Then what about the field intensity inside the sphere? It is very simple. It is very clear that we already discussed that point as the field intensity inside that one is 0, since there is no charge is located inside the sphere. Whenever there is no charge, there is no field intensity. So for x less than r, I can say E is equals to 0. So this is the inside, this is on the surface, and this is the outside at a distance of x, right? So I would just like to draw the graph between the field intensity and the x. I want to notate all these things in a graphical representation when I try chestanu. Just look at it. So on y axis and on x axis I am taking E and x respectively. This is the origin, I can say. So the graph for this one, so at x is equal to 0, which means that if the point P is at the center, the field intensity is 0, isn't it? So as the x increases from the center of the sphere to the surface of the sphere, till then the field intensity is 0. Center of the sphere nunchi surface varaku vachenta varaku kuda field intensity is 0. So that x increases up to a certain point. Let this is the r point. So here I can say x is equal to r. At this point it has some field intensity. Till then the field intensity is 0. So what is the value of this one? k cube by r square. Right? As x increases, still then ఇంకా x increase అవుతుంటే it is inversely proportional to the value of x, right? Right, inversely proportional to the x square. So the graph is something like this. So at r it is having the maximum value. That value is k cube by r square. Okay, so please keep this my diagram in mind. We will discuss in the next class. Okay, coming to the case of non-conducting sphere here. So electric field strength due to non-conducting sphere. So this figure shows a non-conducting uniformly volumetric charged sphere of radius r and charge q is given. So again by symmetry we can say that it in the outer region of the outer region the electric field strength can be calculated by treating its charge at center. So outer the sphere మీరు ఎక్కడ తీసుకున్నా సరే the total charge is supposed to be concentrated at center. అంటే just like in the previous case. In the previous case లో ఎలా అయితే చేసామో ఇక్కడ కూడా అలాగే తీసేసుకోవచ్చు. When we are going to calculate the field intensity on the outer region. So for that I can say that the expression, suppose the point P is located at x from the center. At point P I can say the field intensity, I am taking this one as E out. I can write this one as 1 by 4 pi epsilon naught q by x square. What happens if x is equals to r? Means the point P is located exactly on the circumference of the sphere itself, on the surface of the sphere. So here x is equal to r, substitute I am here. So at the surface I can say E is as k cube by r square. So till then both are having the same kind of expressions. That should be very clear. If x greater than r, so we are saying that k cube by x square. If x is equal to r, k cube by r square. So both are same, is having separate expressions. But whenever we are entering into the sphere, the concept is varying. So for this I am redrawing this diagram in another way, such as, okay, this is the diagram and redrawing this one to find the field intensity inside the non-conducting sphere. So for that here I am assuming a shell, a small part, a shell of a radius of small x, where there is a small charge q is located. So at point P, which is on the surface of the little sphere, shallow sphere, right? This one a very simple one, right? So here I can say that EP, the field intensity at point P, as k into, what is the charge here? Small q by the radius of the sphere is x, so that is x square. Then first I have to calculate the charge, the amount of charge located on the surface here. For that I can take, let it be, this is equation 1. So I can say by symmetry, as we did in the classroom, by symmetry the total charge of the sphere, that is capital Q, by small charge q is equals to the total volume of the sphere, that is 4 by 3 pi r cube whole by the volume of the inner sphere, that is 4 by 3 pi x cube. So by eliminating the proper constants, we can say small q is equals to capital Q into x cube by r cube. So here I got the relation between the small charge q and the capital Q as small q is equals to capital Q x cube by r cube, right? So therefore the field intensity at point P is equals to EP is equals to k q by x square. I know this expression. This implies k by x square. What is the value of q? This one, q x cube by r cube. By eliminating this x square with x cube, by cancelling these two, I can say k q x by r cube is the field intensity at point P. So this is the expression for the field intensity at a given point inside a non-conducting sphere. Okay, sometimes instead of giving a total charge of the sphere, volume charge density given. That is the most important point to be here. The most important you have to remember. So rather than remembering this equation or expression, if the problem is given in terms of the volume charge density, సో ఇందాక మనం ఒక క్లాస్లో చెప్పుకున్నాం, సర్ఫేస్ ఛార్జ్ డెన్సిటీ ఇస్తే అది కండక్టింగ్ స్పియర్గా తీసుకోవాలి, వాల్యూమ్ ఛార్జ్ డెన్సిటీ ఇస్తే దాన్ని నాన్ కండక్టింగ్ స్పియర్ కింద తీసుకోవాలని చెప్పాము. సో therefore the rho is equals to, which means volume charge density, charge upon total volume 4 by 3 pi r cube. This implies capital Q is equals to 4 by 3 pi r cube into rho. Now substitute this Q value in the above expression. We get EP is equals to kx by r cube into 4 by 3 pi r cube into rho. So by eliminating this r cube and r cube, we get 4 by 3 pi kx rho. But what is the value of k? 1 by 4 pi epsilon naught. By substituting that one, x rho by 3 into 4 pi epsilon naught. Since k is equals to 1 by 4 pi epsilon naught, isn't it? So these two are get cancelled. Rho x by 3 epsilon naught is the right expression for the field intensity at point P inside a non-conducting sphere. This should be remembered. In fact, we are going to discuss the numericals part of this one, which are given in a previous examination for JEE and NEET in the classroom, right? So again, I would like to draw the graph between the field intensity and x in case of a non-conducting sphere, such as in the previous case. So consider the field intensity on the y-axis and the the x is taken on x-axis, right? E is given here. So at the center of the sphere, it is at x is equal to 0, again the field intensity is 0, isn't it? So here the field intensity is varying with respect to x linearly. As x increases, E is correspondingly increases. Till then the value is, the point is on the surface, circumference of the sphere, surface of the sphere. So that x increases or also increases, E also increases, sorry, E is also increases. So this is the where at x is equals to r, the field intensity is maximum. That value is given by k cube by r square. So and then if the point is outer region of the sphere, the field intensity is gradually decreases, such as like this. So this represents that E is inversely proportional to x square, right? So this is the difference between the conducting sphere and non-conducting sphere. Thank you.